Hello. We've been on a journey now via path integrals, Young-Mills theory, and we've written down a Lagrangian density for a Young-Mills theory now. And I outlined how one might use this Lagrange density after we've done this gauge fixing procedure of Faddeev and Popov to do actual calculations. We have not actually done any actual calculations with Young-Mills theory in this course. And to a large extent, we're not going to do any real scattering calculations because we don't have enough time to then cover the other elements of the standard model, which is the objective of this course. What I will do today is sketch one calculation you can do, very much sketch. The details are left to you, or at least to consult the textbook, on, for a quantity known as the beta function for the Young-Mills theory. This is one of great importance in telling us how these theories behave at high and low energies. So the first topic for today is the beta function. What is it? And then the second topic will be to transition from calculations using the path integral and gauge fixed Lagrangian densities to doing calculations with a non-abelian gauge theory when we use a lattice regulator or cutoff instead. Before we do that, I'm going to say a couple of words on renormalization, the renormalization group equation, and introduce to you an equation that tells us how to run or adjust coupling constants in a renormalizable theory so that you can then match low energy predictions. So if you recall, right, we have this thing this notion of renormalizability. So you recall that a quantum theory is renormalizable. So a quantum theory with Hamiltonian H, depending on n parameters, z1 through to n, and some cutoff that makes it well defined. So such a theory is renormalizable So this theory is renormalizable if it leads to finite predictions for all operationally well-defined observables. So there's no infinities and things you could actually measure in principle. And furthermore, it's not enough that the predictions are finite, but we want that we can always match these predictions by optionally changing these n coupling constants here with no operational meaning. We're allowed to change them as we change the cutoff. So if we have a bunch of operationally well-defined quantities, which are given as expectation values of Hermitian operators, work out their expectation values as a function of these n coupling constants here. And then, remember, we have this idea of the cutoff size. So here the cutoff represents this cutoff here, lambda, is a list of all the degrees of freedom, and Kc here is just like the length of the list. So it's just a convenient number which tells us how many degrees of freedom our theory is specifying. So we work out the expectation values for all our operationally well-defined quantities. And then we set them equal to some observed values. You do the experiment, and then you estimate this quantity here with your experiment. And it's got to be the case that all these predictions match the experimentally observed quantities here. And furthermore, it's not enough that you just match them for one value of Kc. A renormalizable theory allows you to match this fixed set of numbers. These are fixed once and for all by the experiment. They never change. You can match these for all values of Kc by allowing these coupling constants here to depend on this cutoff Kc. Oops. So by allowing these coupling constants to depend on Kc, we can ensure that these predictions are maintained for all values of this cutoff. So that's a renormalizable theory. I'll put in one sentence here. By allowing Zj to depend on the value of this cutoff here. That's a renormalizable theory. Now, it's sort of amazing, as I stressed in previous lectures, that such things could exist at all. They do. I've given you some arguments, but by no means proof, that phi-4 theory is a theory of this nature. So in phi-4 theory, there are 3 coupling constants, Z1, Z2, Z3. And by adjusting them as you change the cutoff, as you introduce more degrees of freedom, you can maintain your predictions, and you can maintain them as equaling some experimentally determined quantities. There are other renormalizable theories. There's a list of them, and non-abelian gauge theory is one of them. Now, there's one concept that I didn't really stress in previous lectures, and that is what is the dependence of these coupling constants on the cutoff here? Could you even compute that? Is it possible to compute how Zj depends on Kc? This is the question for today. And it's not one whose solution is obvious, I would claim. I mean, it's not clear, apart from sort of brute forcing these predictions here by using divine insight to solve your theory. It's not clear how you would find the dependence of Zj on the cutoff here. Turns out you can do it using perturbation theory for many models, and that's something that I'd just like to outline to you today here and give you the results for various theories that you've now already met. So what we're going to do is we're going to introduce a specific set of quantities that play the role of these AJs here. They're not directly observable, so this is slightly non-physical, I guess you could say. So we're going to apply this constraint here to Green's functions or endpoint functions. That's our task for today. So in place of this, I'm going to write down the Green's function, or the Green function, that you get for n, I guess m now, field operators. What is this? Well, we've met this object throughout our studies of quantum field theory. It's just the time-ordered correlation function, m. Now, oh yeah, I didn't stress where the dependence on the parameters is. Of course, the dependence is in in this dynamics in here. So I will write, and the ground state. So the ground state of our theory obviously depends on these coupling constants Z1 through to Zn and the cutoff. Z1 cutoff. So that's one place where the coupling constants and the cutoff appear in the exact expression of this vector here. And also in the dynamics, right? So this is defined, phi hat x is defined to be e to the minus I h. Now h depends on all these parameters. And t, and then blah, 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 blah. So the coupling constants Z1 through to Zn and the cutoff appear all inside this expression here, both in the vacuum vector of the cutoff theory and in the dynamics of these field operators. These are not at the same time slice, so h will appear, and h then depends on these coupling constants. There's an n here. Z1 and the cutoff. So this whole expression, this green function here, depends on all these things. Now, of course, the green function is not directly itself observable. It's not the expectation value of a Hermitian operator, necessarily. Not necessarily, right? Because if you look at this thing here, that's not necessarily a Hermitian operator. Just take the dagger and you don't get the same thing. But it's near enough, right? So this whole philosophy here could be applied to these functions. And of course, once you know these functions, then you have determined all the observables of your theory. They're just going to be expressed as functions of these Green's functions here. So we're going to do a slight change of what we said here in this definition. Instead of saying that a theory is renormalizable if it leads to predictions that don't depend on the cutoff for all operationally well-defined observables, we're going to change operationally well-defined to Green functions. It's a small change. If you are uncomfortable with that operational, this sort of drop of the word operational, then I invite you just to calculate the actual endpoint correlation function predictions you'd get from interference experiments and then do the same argument. You would get the same answer. Now, there's something really amazing that we can do, and this is such a powerful idea in renormalization theory. So it's this cutoff Kc here is usually a continuous parameter. I mean, not always, right? Kc is this thing that quantifies how many degrees of freedom our theory pertains to. It's not always continuous. There exist theories you can write down where the natural Kc would be discrete, usually with the theories on lattices. It's not entirely. Sometimes it's convenient to allow this Kc to be discrete, but almost always in quantum field theory, this Kc is continuous, and it is just the maximum momentum. So it's usually just the maximum momentum that your theory is allowed to have. The maximum momentum mode that could appear. And I'll write or similar. We'll actually see in the second part of today's lecture that Kc will equal something in real space, namely the lattice spacing, but that's by the by. Now, when you see something continuous, it's a good thing in physics, almost always, if you see a continuous parameter, to imagine changing it a little bit. And when you change something by a little bit, then you can usually differentiate. And differentiation is a good and easy thing. This is the general moral of things that depend on continuous parameters. So if you have some function of a continuous parameter, it's almost always a good idea to use the fundamental theorem of calculus. and express your function in terms of the derivative of f with respect to that parameter. It's almost always a good idea. Because derivatives are easy to deal with, and it's often easier to think about changing something than it is about calculating a thing. And that's exactly what we're going to do here. We're going to imagine, that's sort of an aside to remind you of some basic calculus. We're going to apply precisely this philosophy to the Green functions. We're going to say, what happens if we have the Green's function? Suppose we work out the Green function for some value of kc, and then we change kc just by a teeny weeny bit. What happens? So we're going to look at dg, the change in the Green's function, the endpoint Green's function, as we make a change of the cutoff kc. So how does the Green function change? Well, the Green function depends on kc, so it better be the case that as you change kc, there's some change of the Green function directly depending on kc. But also there's other dependence of the Green function under a shift of these coupling constants. If you were to independently shift the coupling constants, this is how the Green function would change. So let's imagine we've just changed kc by a little bit and the coupling constants by a little bit. So now here comes the important observation. If this quantity is to not depend on the cutoff, right? We don't want the Green function to depend on the cutoff. That is stupid. If it depends on the cutoff, then that means that there's this arbitrary number that's up to our mood on any given day, what it is equal to, and therefore what predictions our theory are equal to. So it better be the case that if we change the cutoff, and these variables here depend on the cutoff, that this increment here is 0. We want that as we increase the cutoff, say, and if zj kc and if these variables zj are chosen to depend on kc in such a way to fix the Green function, which is basically the observable of our theory, then we'd want that this prediction doesn't change. And what does not change mean? Not change means that that better be equal to 0. So I'll write that down here so that it makes logical sense. So it's a simple equation, right? It just tells us that the partial derivative with respect to zj, when these zj's obey the correct dependence on the cutoff, plus the direct change of the Green function in terms of the cutoff, that together they should be 0. Otherwise, it wouldn't be renormalizable. So this is an equation. This is an equation that you can work with and calculate. And what we usually do is multiply we're going to multiply by kc the left-hand side and right-hand side. And then this equation becomes for convenience, we're going to multiply by kc on left-hand side, and right-hand side we're going to divide by dk. So we end up with this expression here. Now, we can make that a total derivative. And we're going to give this thing a name. This is called the beta function, beta j k c. And then this gives us an equation. It's a very special equation. So this equation here expresses in infinitesimal form precisely the statement that Green's function shouldn't depend on the cutoff as you change the cutoff in a renormalizable theory. Now the reason for this multiplying by kc is that we're doing a change of variables to exponential coordinates. It just makes, in applications, it's just typically easier to work with exponentials of the cutoff, or in this case, logarithms of the cutoff, than it is with the cutoff itself. Because this kc is usually attached to scale, and a scale transformation is implemented exponentially. So if you wonder why I did this, later on in applications, when you study these things, you'll see that it has to do with scale changes. So once you know this beta function, beta j kc, then you basically know zj. You know zj because all you have to do is integrate a differential equation to get zj. How do you get it? You just solve this equation here. So we could have just directly worked out zj. We could have worked out how does zj depend on kc to make the green function not depend on kc. However, this route here is typically how we work out the dependence. And this is how you will see it quoted in quantum field theory textbooks and on theoretical papers. The dependence of the coupling constant zj on the cutoff will usually be quoted in terms of how does this beta function behave. And that's how this beta function is defined. So now I'm going to mention 3 examples. Oh yeah, about massless theories. A question?
Yeah, could it be that there is a differentiation with respect to ZJ in the middle equation?
Oh goodness, yeah. Okay, the question is, shouldn't this be a derivative with respect to Zj up here? Yes, that should.
The line below, right behind the beta, there should be, there behind the shell, should there be a derivation as well?
Oh gosh, yeah. All right, there should have been a derivative here. I was missing from that part there. Yeah, it looked a bit simple. So there's a slight modification we have to make for theories without a mass. Okay, the usual way we impose that the predictions of our theory matches an experimentally observed quantity for massive theories is we usually demand that this two-point function here in momentum space has a pole at the physical mass of the particle of the theory. That's just the usual practice to determine the experimental, to fix our observations. But there's a problem when the theory is massless. And that's we're going to encounter in the rest of our course several massless theories, so we have to be a bit careful. We get extra divergences for massless theories. We can't do this basically. I won't go through the details of the kinds of divergences that you encounter, but if you try and fix this equals 1 on p, so something with a pole at 0, then you encounter infinity equals infinity in some equations. So to be a little bit more careful. And so there's a kind of compromise that people use, it's usually employed, and that is we demand that this thing, that the two-point function has a pole at a negative space-like momenta. That's how we deal with the massless case here. We insist that this thing has a pole with a space-like momenta. And that will lead us again to finite quantities. And then we let Kc go to infinity. And so then this will then reduce to the green function for a massless theory. Okay, so that's just an additional subtlety that you'll see. And so in textbooks, Kc usually equals big M. They call big M the scale at which they impose this extra condition here. So divergence is perhaps not the right word. It just means that to fix predictions against experimentally observed quantities, you encounter expressions like infinity equals infinity, so they're just not well defined. So beware, massless theories have this extra subtlety, but otherwise everything proceeds just as for massive theories. Now, I'll give you some examples of these beta functions that you'll see quoted about. So you don't see, for a given theory, you don't see the running of the coupling constant in terms of the cutoff. Usually it's quoted in terms of z. You see it quoted always in terms of this beta function. And so I'm going to give us some examples. Now in phi-4 theory, we kind of already sort of did do the calculation. If you work out the divergences of phi-4 theory and then you work out how to cut off that theory and then you work out how the counter terms change and you see that the beta function, which is how this lambda parameter should shift as you change the cutoff, is given by this function here. Now, for quantum electrodynamics, we haven't done the calculation. Quantum electrodynamics is an abelian gauge theory. It has one coupling constant, E, the charge. And when you work it out, you get this answer. You can work all this out to first loop order. It's the first place where divergences appear. And the big one non-abelian gauge theory, this one you can also work out the beta function, or at least show you the diagrams you need to analyze. So in non-abelian gauge theory, we have one free parameter, this G, and we also have to allow it to run in order that the predictions of our theory don't depend on the cutoff. And that running, you can work it out by analyzing the divergences of a bunch of diagrams and summing them together. So this is actually rather interesting. So I'll draw out the diagrams here that you have to study. You have to study this one. This is the first diagram that has a divergence and is a gauge boson going to a gauge boson. So if you use the Feynman rules, you'll be able to write down integrals for each of these diagrams. It's another diagram at second order. Here's a diagram at first order that contributes to this process. And then we have one more that can happen, and that's this ghost diagram here. So you analyze the divergences of this process here, the process for a gauge boson to go to a gauge boson, just the propagation process. That's actually massless. This gauge boson has no mass. So we have to use this prescription here to fix it to equal to some experimentally determined quantity. This will then tell you how a bunch of counter terms have to behave, or in other words, how ZJs have to behave, or how betas have to behave. But this doesn't quite completely specify the dependence of the coupling constant on the cutoff. we need to analyze some more processes. We have to also study the probability for a fermion to propagate, for a quark to propagate. And we have to also analyze, we're still not done. We have to analyze this process as well here and demand that that's equal to some experimentally determined quantity. And only once you've done all these diagrams do you find out how the counter terms depend on the cutoff. And then, and only then, do you work out the beta function. So this is a calculation that goes over some, I don't know, let's say 5 or 6 pages, the A4. Right. So if you look at each of these diagrams here, they're integrals. The integrals you can do, and they all diverge when you take the regulator away. Now we're using this dimensional regularization trick that I mentioned a couple of lectures ago. If you use that for each of these diagrams here, then at least Lorentz invariance is maintained. So use dimensional regularization for all these processes here, and you insist that they lead to finite quantities. And then that tells you how the counter terms in your theory have to change, and the change of the counter terms tells you in turn how the coupling constants should change. And there's only one coupling constant for non-abelian gauge theories. And so after all the calculations get done, you end up with an answer. And this answer was a rather remarkable answer. We end up with this answer after you've worked out all the details. It's a good project at the end of this course to go through the calculation of all these diagrams and ensure that that you match all the divergences and lead to finite quantities, especially this diagram here. That's the interesting one with the ghost in it. And you learn that this beta function depends on the gauge group. There's actually an on 3 times n here. That's SUN. And it depends on the numbers of fermion families that you have. So if you have like 1 fermion, then this is minus 2/3 and so on. And the important thing to note is that if your number of fermion families is small, the beta function is negative. And this is a very dramatic observation. It says that as you raise the scale, the energy scale that your theory is meant to deal with, then you can effectively, I mean, as long as this is minus here, then the way the coupling constant G flows with the cutoff, the energy scale you're looking at, is that it gets smaller. G gets smaller as Kc goes to infinity. And that's kind of amazing. What is this saying? This is saying that as you take the cutoff away, and your theory pertains to higher and higher energy processes, that effectively your theory, no matter how big no matter how big G was at the beginning, so if G was like, for a low energy effective theory, if G was enormous, like 100 or something, as long as you deal with processes that have high enough energy, G is effectively very small. You can model the dynamics with a very small G, and you can use perturbation theory. This is called asymptotic freedom. Oops. All right, this is a really important observation. It's one that's allowed us to do calculations with this particular theory. Because before the advent of computers, before they were fast enough, we didn't really have a way to solve non-abelian gauge theories for low energy processes. Because the effective theory that models a non-abelian gauge theory at low energies, that effective theory has a huge coupling constant G for the degrees of freedom that it pertains to. But as you increase the cutoff, as you increase the energy scale which your theory describes, it can be modeled with an effective theory where G is much, much smaller. Much smaller. It can be made as small as you like. So as long as all your intermediate processes sort of see the whole energy range, then effectively you can work with an almost free theory. So this is what this asymptotic freedom definition is pertaining to here, that you can use perturbation theory for high energy processes. A rather extraordinary observation. So this is not something that's generic. The theory of QED, for example, is the exact opposite, right? If you want to look at high energy processes, then the effective theory you need to deal with has a larger coupling constant, and you can't use perturbation theory. So this is the exact opposite here. Now, this isn't a proof that this theory has this asymptotic freedom, but it's a big hint, because even though G gets smaller as the energy range is increased, that doesn't actually mean that perturbation theory is any more valid than it was before. So we always have these standard complaints about perturbation theory that I mentioned last semester, that we're perturbing unbounded operators with unbounded operators, blah, blah, blah. That doesn't matter because people have done the perturbation theory, they've matched the predictions with the experiments, and they work very well. So at the stage that we are at, where we can use perturbation theory, this works extremely well. This idea of modeling high energy processes using perturbation theory works extremely well. But there's one regime where it works extremely badly, and that is low energy. So, of course, high energy processes is good. That's what we see in particle accelerators. Before I move on to low energies, you get very, very hot, fast particles and you smash them against each other, and that's a high energy process, right? You put in tera electron volts, giga electron volts, boom, smash them together, and then you should be able to use perturbation theory to get really reliable predictions for what happens from non-abelian gauge theories for this asymptotically free theory. Works really well. However, there's one place where it works particularly badly, perturbation theory for non-abelian gauge theory, and that's for the low energy part of and that's what I want to tell you about today. There's a whole other way to talk about non-abelian gauge theory that's appropriate for the low energy sector. That's the sector that pertains to our everyday life. So we usually don't run around at near relativistic momenta and smash into each other. That's not how we experience non-abelian gauge theory in our everyday life. We usually have very low energies. We're at non-relativistic energy scales. And there, we should study our gauge theory in the low energy limit to get predictions. The predictions we're interested in there are like the masses of particles, the rest masses of particles, because that's the things that occur in everyday life, not particles with relativistic momentum. And the whole infrastructure that we built via path integrals, Faddeev-Popov, gauge fixing, blah, 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 that is exactly not going to work for this low energy sector of this theory here. So this argument here is only useful for high energies, the perturbation theory. For low energies, we need something different. We need a new cutoff. We need a new idea. And I suppose this new idea is rather old now. It's 76, I believe. I forget. Due to Wilson. So if you ask a journalist, a science journalist, who the great physicists of all time were, they're likely to give a laundry list of people like Einstein and Feynman and other relatively well-known figures. But the real heroes of high-energy physics, some of them are hardly known at all. One of the greatest of them all was Wilson. So Wilson's name has actually occurred several times in this course. Wilson's responsible for our current understanding of the renormalization group and effective field theory. Wilson's also responsible for this lattice formulation of non-abelian gauge theory that I'm going to describe to you today. And he's responsible for a whole lot more besides. So Wilson is one of the true giants. But you won't read any sexy autobiographies of Wilson. He was a quiet fellow who then became an educator in later life and who did amazing things. So this new idea of Wilson is to use a lattice regulator. Okay. It's not so deep, right? Put it on a lattice. But actually it's pretty challenging to put a non-abelian gauge theory on a lattice, and that's due to local gauge invariance. Very challenging. And it's challenging because the gauge group acts in this slightly non-local way, right? It takes the gauge field to the gauge field plus something, a derivative of something. And I'll just look up that derivative of something that it takes it to. Just so I don't write the wrong thing. Yeah, here it is, right? So if you remember the gauge field, you usually express it in terms of these sigma matrices here. Under a gauge transformation, it changes mostly, but not completely locally. That's the bad bit there. So if you discretize things onto a lattice, so if you discretize this gauge field onto a lattice, then what is to become of this transformation here? Well, one obvious answer is you discretize that derivative there as well. But sort of down that road lies lots of complications. So it's difficult. It's not going to work so trivially that way. So Wilson's idea, it's very beautiful. Wilson's idea is to say, well, the actual things that we really cared about wasn't A anyway. The things we cared about are parallel transporters. So these parallel transporters, they're the things that allow us to define derivatives. So maybe the fundamental degrees of freedom of a lattice approximation to gauge theory isn't the gauge field on a lattice, but rather the little parallel transporters themselves. So the idea of Wilson is a lattice approximation to a gauge theory. What really matters are these parallel transporters here, which are elements of the local gauge group, which for us is SU2, although everything I say is true for other local gauge groups. Is that these are the fundamental degrees of freedom, the parallel transporters that tell you how to get from site J to a neighboring site. So if you draw the lattice, here's lattice site J, and we have a parallel transporter that tells you how to transport a fermion across one lattice unit. lattice spacing is epsilon here. And that's u, j goes to j plus in the x direction, let's say, which is 1. And then there's also a parallel transporter that tells you how to get from there to there. And that's u goes from j to j plus the 0 direction. This is a time, this is a space like this. So the fundamental degrees of freedom of a lattice theory that's meant to be gauge invariant should be parallel transporters that take you one lattice cell across. And then you can build bigger parallel transporters just by multiplying. So the parallel transporter that goes from j to j plus 2 epsilon mu is equal to first go to epsilon mu, then go from epsilon mu to epsilon mu plus 1. Epsilon mu plus 2. Epsilon mu. Blah. Oops. Or e mu. I said epsilon, but I meant e. So these are elements of this group here. They're like matrices, right? 2 by 2 matrices for SU2 gauge theory. And so Wilson's proposal is that in lattice gauge theory, the fundamental degrees of freedom are a list of 2 by 2 matrices, one per link, one per edge of this lattice here. This is all classical so far. So this is something that lends itself very beautifully to doing it on a computer. If you choose a lattice, say 4 by 4 by 4 by 4, you could just about store that on a computer. You could just about store 4 to the power 4 2 by 2 unitary matrices in the computer's memory. It's not so bad, right? So And so the state of the art, I understand, is roughly 10 by 10 by 10 by 10. So if you estimate this number here, it's 2 to the 8, right? 2 to the 8 double precision numbers, roughly speaking. I believe 4, 8, 16, 32. I think, yeah, it's 250, roughly 1,000 numbers, right? 1,000 floating point numbers in a computer's memory. So today that's laughable, right? We can do that pretty easily. But back when Wilson wrote his paper, 1976, I believe, Confinement of Quarks, I think is the name of the paper. That was pretty serious, right? RAM was not very cheap in 1976. And a kilobyte, like if you think about the Apple IIe and the other computers that were coming out around that time, you know, a kilobyte was not a cheap piece of, not a cheap microchip. So that was close to the limit of what you could do. So you could store the classical configuration of a gauge field on a lattice, on a 4 by 4 by 4 by 4 lattice. And you could just about do it. And he did it, right? Wilson was very proficient with computers. He had a PDP-11, I believe. I don't know, I didn't research this. I just remember this. And he coded all this stuff up on punch cards. But for the time, this was like amazing, you know, to have 1,000 numbers. And then, okay, so that's great. So you can store something that looks like the configuration of a gauge field in a computer. And now, you know, nowadays we got a factor of, let's say, 6. So we can probably store without many difficulties, what? So if we do, say, 16 gigabytes before things blow up when you do matrix multiplications, what's 16 gigabytes? That's 16 by 2 to the... What is 16 gigabytes? Does anyone know what a gigabyte is, roughly? 2 to the power of... So a kilobyte is 2 to the power 10. So then 30. I'm hearing 30. Yeah, I can't do it in my head. Roughly 2 to the 30. So that's sort of, that's reasonable. And if you divide that by 4, that's approximately 2 to the 8 by 2 to the, yeah, right. So actually you can do kind of bigger, right? Do lattices that are roughly 2 to the 8, it's sort of 256. It's not bad. And it's all classical. How do we do quantum mechanics? So classical gauge theory we can do pretty well now, like relatively large lattices. But how do we do quantum mechanics? Well, Wilson's idea, and not the one that we'll pursue, but Wilson's idea, was build an action and sample the path integral, Monte Carlo sampling of the path integral. So this is the way we're doing computations to this day. I'm not going to tell you about the details of Wilson's direct approach. I'm going to tell you about an alternative approach, one that I see is slightly more promising now that quantum computers are on the event horizon. So Wilson, his original idea was to build an action that somehow models abelian gauge or non-abelian gauge theory, and then sample this path integral over this list of numbers here. Now, if you do a path integral in real space, real time, sorry, Minkowski path integral, then you get lots of minus signs, and there's no hope of this working. So what he actually did is he did a Wick rotation first, and then looked at this integral here and says, well, what's this integral equal to? You know, U here is this list of 2 by 2 matrices. So you randomly generate 2 by 2 matrices according to this probability distribution here, and generate enough of them, build the empiric average, and then you know what that integral is. You can code it up sort of in an afternoon, it's not so difficult, but to get it to work for these mega lattices like this requires some extraordinary genius. And that's what a lot of the effort is being focused on today in low energy calculations, is finding ways to very cleverly sample this path integral here when you've got lots and lots of random variables. And so the action that Wilson chose is a sum of plaquettes of something called a Wilson loop. So you look at the lattice here, and then you build the following object. You take the parallel transporters going from here to here, from here to here, from here to here, from here to here, multiply them all up, and take the trace. And that's a thing called a Wilson loop. I'm not going to go into the details of this because I'm going to show you something else, but this is the idea behind Monte Carlo calculations with non-abelian gauge theory. You take these Wilson loops, that creates a probability distribution for these U's. You sample from that probability distribution using Monte Carlo sampling. And I mean, the first thing you can try, you can do it this afternoon if you want, is you work with the 3x3 lattice and use rejection sampling to do that. You know what rejection sampling is, right? You just throw it out if it's not correctly sampled. And then you can estimate this integral here. Now, of course, you have to be 10 times more sophisticated if you want to get to lattices of this size here. And the remarkable thing is, when you do this, you get results, and these results match the predictions for low energy processes in non-abelian gauge theory. So we really think we're on the right track here. One comment on this action here, why use this? Well, this is none other than the holonomy, right, around this plaquette here, and the covariant derivative, which is the object that gives dynamics to the degrees of freedom in non-abelian gauge theory, arises from the small plaquette limit of that quantity there. And the other beautiful thing about the Wilson loop is that it's locally gauge invariant. So if you do a gauge transformation, this quantity does not change. So that's the general story of lattice gauge theory. I'm not going to tell you about lattice gauge theory in the path integral picture. Instead, I'm going to tell you about the Hamiltonian version of this in much more detail. Because, well, you know, comment the first, this has been extraordinarily successful. This is the best way we know to get non-perturbative answers from quantum field theory is via this approach here. There's no doubt this is the best way. But it does have some awkward downsides. One is that you're calculating processes in imaginary time via this Wick rotation, which is roughly equivalent to doing statistical mechanics with these gauge theories. So we're talking about processes at some temperature rather than real-time processes. So this way of sampling path integrals doesn't work very well when you want to calculate time-ordered correlation functions, or you want to calculate processes that depend on time. So scattering processes are a bit harder. This method also isn't in any way obviously a quantum theory. You know, what would guarantee that this theory here gives rise to observations that come from a quantum theory? It's not clear. I mean, it does, but the quantum nature of the whole theory is thrown out at this stage here when we do this sampling over classical configurations. So there's this alternative way to build a lattice-regulated non-abelian gauge theory in the Hamiltonian picture, where at least you know for sure that you have a quantum theory from the beginning to the end. So everything's unitary, there's no problems with signs and so on. I mean, it has some downsides, namely that it's not so easy to do it on a normal computer. It's not so easy to simulate Hamiltonian lattice gauge theories on a normal computer, but they lend themselves particularly well to quantum computers. So what I'm going to show you is kind of like, if you like, the next generation of lattice gauge theory, what it might look like once we have large-scale fault-tolerant quantum computers. So given that we don't have a large-scale fault-tolerant quantum computer, you'd be inclined to be skeptical. That's fine. But if you're an optimist, this is possibly the way we'll be doing gauge theory calculations in the future. So I'm going to spend the rest of this lecture and the next lecture telling you about Hamiltonian lattice gauge theory. Very exciting topic, in my opinion. Ah, 1974, not 76, sorry. So the theory I'm going to tell you about is due to Kogut and Susskind. tell you the year as well. I think it's 78. Can't see it. All right, I can't see the date. I haven't written that down. So Kogut and Susskind developed a quantum theory. This is a legitimate quantum theory. They proposed it's 1970 question mark. It was only a year or two after the original one, so I'm thinking it's probably 78, but it might be 76 or 5. Okay. Okay, this is what they did in this paper. It's a very beautiful paper. It's extremely readable. You only need to know about the quantum mechanics of angular momentum to be able to read this paper, as we'll see. And what they proposed is a quantum lattice theory. So it's a theory of a lattice, which they argued, they give good arguments, should reduce as the lattice spacing goes to 0 to normal Yang-Mills theory. Now the word that I want to circle here is this. So it's a Hamiltonian theory. They gave a Hamiltonian for it and a Hilbert space for it. Now, in keeping with the way that we should be thinking about quantum fields, this is ultimately, I'd argue, the right way to define Yang-Mills theory. So we shouldn't define Yang-Mills theory as the quantization of some classical field theory. No. That's I've argued multiple times that quantizing a classical theory isn't the right way to give you a quantum theory. What you should think of as a field theory is the limit as the cutoff is removed of some finite quantum theory. So this quantum theory that Kogut and Susskind wrote down is finite. All the predictions it gives are finite, so it's perfectly cut off. No difficulties with the theory itself. And as you reduce the cutoff, its low energy effective theory should be Yang-Mills theory. They argued that, they haven't proved that. In fact, if you could prove that, you'd earn yourself a tidy $1 million. So there's, well, you'd also have to show that the low energy limit has a mass gap as well. But if you could do that, then you've solved a major open problem in mathematics. But at the level of physical rigor, certainly the argument is very compelling. I don't see any reason to doubt that this theory has as its low energy effective limit Yang-Mills theory, as the cutoff is removed. So this is a definition of non-abelian gauge theory that works. All right, so I better tell you, what is this theory? Well, it's a theory of a lattice, right? So degrees of freedom do live on the lattice. I mean, it's a quantum theory of degrees of freedom living on a lattice. So for every link, we associate a 2 by 2 unitary matrix. This is no different from Wilson's formulation at this point here. But remember, Wilson's formulation was classical. So the degree of freedom was just a classical degree of freedom, a unitary matrix per point. So the way to quantize this is wave functions. You think of so these unitary matrices here, they're elements of SU2. So they're just like a point in this space SU2 per link. The quantum theory is the simplest way you could imagine quantizing a classical variable that lies on SU2. So if you have a particle that lies on the real line, how do you quantize it? Well, you quantize it by saying, well, we have this wave function attached to this particle. So if you have a particle in the ring, how do you quantize it? Well, you say the simplest way is you just say, well, I attach a wave function to the ring now. Instead of just one number, I have a wave function. And if you have a degree of freedom, a classical degree of freedom, which is stuck in this manifold SU2, and you say, how do I quantize that? Well, the simplest thing would be to say I have this wave function that's none other than just some function from SU2 to the complex numbers. So these wave functions, so per link, psi is an element of the square integrable functions from SU2. These wave functions have to be integrable so that they give us probability distributions when we integrate over the circle, the line, or SU2. So per link, psi, the quantum degree of freedom of our lattice, should be an element of the square integrable functions on SU2. Now the square integrable functions on SU2 is a Hilbert space. I'm just going to write it as H. What notation am I going to use for links is the question. I'll use all right. I've used E in my notes, which I realize is a really stupid notation, given that I've used E in different contexts. I also don't like big L. What letter to use? J, K, L, M. I'll stick with E. So per link E, the quantum degree of freedom is a wave function in some Hilbert space, HE. And it's the Hilbert space of wave functions on SU2. Now SU2 is diffeomorphic to the 3-sphere, not the 2-sphere, the 3-sphere. So that's a useful fact to know. So you can think of, without harm, the quantum degrees of freedom of our quantum lattice gauge theory as wave functions on the 3-sphere. There's absolutely no harm in thinking about it like that. And so wave functions on spheres, that's something that you should sort of ring some bells. Wave functions on spheres, you think of spherical harmonics, you think of angular momentum, and you realize that actually you have, from studying the hydrogen atom, basically all the material you need to understand this Hilbert space L2 of SU2. I'm going to write out some facts about this Hilbert space in a second. So the total Hilbert space that this Hamiltonian of Kogut and Susskind will pertain to, that total Hilbert space is just the tensor product over all the edges or links in the lattice of this HE. That's the Hilbert space. So we've done the kinematics. That's already done. Well, I'm kind of lying, right? Because we're not going to be looking at this total Hilbert space. There will be configurations here that are equivalent, because we want that our theory is gauge invariant, that it exhibits the symmetry of gauge invariance. We'll see how that arises soon when I talk about the gauge group. But for now, the total Hilbert space of this lattice theory is this Hilbert space there. Now this is very boring. If I tell you the kinematics of a theory, that tells you nothing except what the configurations are allowed to be. It doesn't tell you anything changes in time. So we want to build a Hamiltonian for this Hilbert space that should in some sense reduce to Yang-Mills theory when you take the lattice spacing to 0. And to build that Hamiltonian, I'm going to introduce a couple of operations on this Hilbert space. So we're going to write so just as you would, if you have a particle on the real line, then you can specify its state with a wave function. A wave function is a function from the real line to the complex numbers that's square integrable. But you can also write it as a ket. And the way you write it as a ket is you use a position basis, right? So if you just imagine for the moment that u is like a number on the real line, then I've just written down the ket associated to the wave function psi of u. And this is the position eigenvector here. Now, for us, u is not an element of the real line. U is an element of SU2, which I've told you is the same as an element of the 3 sphere. So you just need to know 3 coordinates, and then you know what u is. And we're going to define this position basis just with a Dirac delta function, right? I'll put scare quotes around it because it's not strictly correct. And I often don't bother with coordinates. We just say that u is an element of SU2. U is a 2 by 2 matrix. It's a list of 4 numbers, or 3, because we've got this determinant condition. So you can think of this as a definition of the ket associated to this wave function psi there. And we're going to introduce our first operator on this Hilbert space called left multiplication. So L of u of psi is defined to be this, to have this action here. So it takes, if you like, I could have just defined it in terms of these position eigenkets. Left multiplied by u takes the ket v to u times v. So this is also an element of SU2, right? If you take two by two unitary matrices and multiply them, you get another 2 by 2 unitary matrix. And so this is actually the analog of just shifting in the real space Schrödinger picture. So in Schrödinger mechanics, if you want to shift your system by x, then you multiply by e to the ix p hat. P hat's the momentum operator. So L of u is just like that. But because things don't commute now, these coordinates don't commute, then there's another operator, R of u, defined in a similar way. It's VU dagger, I believe I use dagger. Although I don't have to. Yeah, I use dagger. There you go. So there's the other shifting operation. So this is different a priori, right? You know, if I multiply on the right by u or on the left, I might get different answers, especially with that dagger. So these are two analogs, if you like, of e to the ix p hat. And why do we define these things? Because they give us the momentum operators. I'm going to tell you about that in the next lecture. So to get the momentum operator, one way to define the momentum operator is to say it's that thing that you get from the shift as you make a smaller and smaller shift. You differentiate with respect to x. That's the momentum operator. And we need a momentum operator for our lattice theory in order to give it a dynamics. And the way we're going to do it is by taking these left and right multipliers and differentiating them with respect to u. And that'll give us some momentum operators. And that'll be our first step to building a quantum Hamiltonian for this lattice gauge theory. We don't have time to discuss that today, so I will tell you about that in the next lecture. So for now, I thank you very much.